Hello, welcome back to my channel, and in this video we're gonna learn about Ernest theorem. Okay, so one of the things you learn in quantum mechanics is using expectation value. But why do we use expectation value? Why not use these mode, mean, and all other things if we wanna use because expectation value can be tricky. But this is kind of a motivation why we kind of use expectation values, because Ernest theorem states that the expectation values obey the classical laws. What I mean by that, you know that the rate of change of momentum is equal to force, and this is one way of writing. Force is also negative of gradient of the potential, and this is one of the classical laws in physics. And Ernest theorem states that the expectation values obeys classical laws with some approximation. So now let's prove the statement where say Ernest theorem says that expectation values obey classical laws, and we can use our the same thing that theorem state with the rate of change of momentum. So we have this definition of momentum that we calculated in our previous videos, and now what we're gonna do, we're gonna take the derivative, and because we want to find the rate of change of this expectation of this momentum. And you can when you take the derivative, you can take the derivative inside that we learned in a previous video. And now what we're gonna do is we're gonna apply the chain rule, as this is quite common at this point. We have done this calculation over and over again. Now we apply the chain rule, right? Now you have this d psi over dt and d psi over dt on two of the side, and we're gonna replace d psi over dt using the Schrodinger equation, and we're gonna substitute these two equation in our the Schrodinger equation. We're gonna get this value from the Schrodinger equation, and we're gonna substitute that in and see what exactly we get. And then what we're gonna do, we're gonna try to combine some of the things. Now we can distribute all these. Now we're gonna substitute these things, and we can also take the derivative with respect to x of this whole thing inside the parentheses, and then we can rearrange things. And I would highly recommend you do it on your own. If you're listening to or doing if you're seeing someone doing math, is not a good way to learn. Or quantum mechanics, if you want to learn in a mathematical way, I would highly recommend you to do this on your own. You will get a better understanding. Then what you can do here is now substitute do all those calculation and try to rearrange things, get all the potential term on one side and get all the other terms in one side, and that will help you in the next step. What we're gonna do here is, and now what you can do here is, you have this term. What you're gonna do, you're gonna apply chain rule twice, and you're gonna find out this term goes to 0. And I would highly recommend you do it on your own, because it's a long process and I don't want to do it. And also it's a good practice you're gonna get by learning all this chain rule that we have practiced in our previous videos. And you're gonna apply chain rule like twice, and this term is gonna integrate to 0, right? And then we have this term, and what you can do here is simplify this term. Now you take the chain rule of the second term, and then you substitute all this in, and these two things cancels out, and you are left this term, and this term cancels out, and you're left with this equation. And you have the equation. Now you can substitute all this expression in your integral, and you are left with this is what will be the expectation value of your rate of change of this potential. And this is what the Ernest theorem. So what Ernest theorem does is it bridges the gap between quantum and classical mechanics. It shows that quantum mechanic averages follow classical laws, but only approximate. This is one of the theorem that you learn in quantum mechanics. So I hope you like this video. If you do, give the thumbs up, and I will see you next.